Hi, here's Mark Dubois from HaroUT. In the present video, I use one of the examples provided with the HaroUT library version 1.1 to show the use of the detection and synchronization gates and of the Time-Compensated-Gain or TCG with the Olympus Focus PX. Once the library has been installed, you can access the examples by going to the Help menu and select Find Examples. In the Example Finder, search for the term HaroUT. There are 5 examples with version 1.1. 2 are generic and 3 are examples related to the Olympus Focus PX. Let's select Olympus, Example, Gates, and TCG. On the front panel of the example, there is an area for the TCG parameters. Those parameters are a depth array, a gain array, and an enable checkbox. The synchronization gate area contains 3 parameters: start, length, and threshold, along with a enable checkbox. The detection gate area contains the same parameter than the synchronization gate area, in addition of a type enum. Let's have a look at the block diagram for each of those functions, beginning with the TCG. The code architecture of this VI is a single loop state machine with an event structure in a wait for event state. Upon a change of the enable TCG checkbox, the TCG is enabled or disabled on the Focus PX using the set TCG function according to the new value of the enable checkbox. When enabling the TCG, the depth and gain arrays are used to set the curve of gain as a function of depth. The depth values are converted to time using the provided material velocity. Notice that the depth and gain arrays must have the same number of elements. If not, the HaroUT server generates an error. The code associated with the synchronization gate is located in another event case. In this case, a change of value of any of the synchronization gate parameters triggers the parameters to be sent to the Focus PX using the send sync-gate function. For the detection gate, as for the synchronization gate, a change of value of any of the detection gate parameters triggers the execution of the corresponding event case. However, for the detection gate, the code is located in its own set soft-gate case of the state machine, because this code is also called from other cases of the state machine. The code for value changes for both the detection and synchronization gates call for the draw gates case of the state machine. The code of this case redraw the gates using a draw gate function for each gate on the graph according to the new parameters. Now, let's have a look at the code that handles the reception of data from the Focus PX. This code is located in the wait for events case and then in the Focus PX data event case. Here, the upper part of the code is to simply calculate the actual average acquisition rate. In the lower part of the code, the received A-scan is converted to depth values using the set-to-depth function. The A-scan is then converted to a graph using the function A-scan-to-graph, and also passed to the loop data for detection gate processing, in the case process SW gate. In the process SW gate case, the detection gate object and the A-scan are passed to the process function, resulting in amplitude and depth values if an echo is detected. Notice that the code here shows how to insert the depth value into a C-scan using the encoder values, even though the present example does not include the full code to handle C-scans. Now, let's go back to the front panel to run the example. Let's start the acquisition. We can see on the A-scan of a conventional UT transducer in pulse echo, the excitation pulse and a first echo from the back wall of the Rexolite delay line. The synchronization gate is blue and the detection gate is red. The synchronization gate is drawn only when disabled. Let's enable the synchronization gate. Now the A-scan starts with the first back wall echo and the synchronization gate is not drawn anymore. Let's change the A-scan start depth to 11 mm to completely skip the first echo and to see both the second and third echoes. Notice that now the depth values of the A-scans are in reference to the echo used for synchronization. Let's change the TCG parameters to make the second echo on the graph bigger than the first one. Let's increase the acquisition duration so that we can see the next echo. Its amplitude is as expected without TCG, because we put zero gain values after the second echo. Negative values of gains are possible with the TCG as long as the sum of the group gain and of the TCG gain is equal to or larger than 0. Let's put the TCG gain for the SIG back to 10 dB and the duration back to 20 mm. Let's explore the different types of detection gate. The first one is maximum, and the detected depth and amplitude are those of the acquisition point with the maximum value above the threshold, as shown here when comparing the blue cursor values with those of the detection. The next detection gate is crossing. For this type, the depth value is the value where the signal first crosses the detection threshold, and the amplitude is the one of the maximum point, as shown here by the red cursor for the depth and the blue cursor for the amplitude. The next detection gate type is first peak max. For this type, the detected depth and amplitude values are those of the maximum of the first peak above the detection threshold, as shown here by the blue cursor. Finally, the last detection type is first peak crossing. The detected amplitude is the maximum amplitude of the first peak above threshold, and the detected depth is the depth where the signal first crosses the detection threshold, as shown by the blue cursor for the amplitude and by the red cursor for the depth. I hope that video helped. If you have any question or feedback, you can go to HaroTech.com or leave a comment in the comment section of this video. Thank you for watching.